3B accuracy and precision in measuring. 3.6 the limits of measuring. Take a ruler graduated in centimeters and measure the length of this. Textbook spine. It should be about 27.6 centimeters long. You may have noticed that the edge of the book fell between 27.5 centimeter and 27.7 inch. But how long is it exactly? This is impossible to answer. If your ruler is a metal, it can expand and contract with temperature differences. If your ruler is wooden, it changes length with humidity. Most plastic rulers came from molds that vary in accuracy. Also, if you measure the book's spine a second time, you might notice that the reading is slightly different from the first, because you placed the ruler 0 mark in a slightly different place. These thoughts show many of the problems of measuring. Measuring can never be exact for one or more of the following reasons. The instrument markings can't be fine enough to align exactly with the dimension you're measuring. Environmental conditions, such as temperature, pressure, or humidity, may alter the instrument's scale. You may use or read the instrument incorrectly. The instrument may be defective from manufacturing, damage, or wear. Conditions during measurement can interfere with obtaining a good measurement. Any of these problems will produce a measurement that is not at the actual, or more correctly, the acceptable value. The difference between a measurement and the dimension's acceptable value is the error of the measurement. Error in measurement is an ever-present fact of science. Every measurement contains error, no matter how good the instrument and the observer are. For that reason, much of the work scientists do in their research goes into figuring how much error is present in their measurements. Even though every measurement includes error, Christians have the good reasons for trying to minimize the error. Measuring is just one aspect of exercising dominion. Without limiting the error of measurements, we would not be able to develop really useful models in science and technology. There would be inaccuracies that could lead us to incorrect conclusions, or things that we build, like the Curiosity rover, wouldn't fit together, right, if builders of different parts use different methods of measurement having different allowable errors. We try to minimize the error in measurement by using instruments that are as accurate as needed and that have the precision required for our work. Let's examine these often confused terms. 3.7 Accuracy. The accuracy of a measurement is an assessment of the measurement error. A scientist would state that measurement is more accurate, less accurate, or just accurate, or inaccurate. A smaller error means a more accurate measurement, while a larger error indicates a less accurate measurement. An instrument's accuracy depends on how well it is constructed and maintained. The scale graduations must be accurately printed or engraved. The instrument's accuracy must not change when environmental conditions change. Most instruments rarely meet these ideals. However, many scientific instruments have built-in features that allow the user to adjust the instrument's accuracy back to within an acceptable range of error. To do this, the user first measures an accurately known object or quantity, called a prime standard, with the instrument. Then the user adjusts the instrument to display the value of the prime standard. The instrument user also affects the accuracy of a measurement. Because of the limitations of human observation, there is always some human error associated with making any direct measurement. Scientists try to eliminate these kinds of errors by averaging several measurements of the same quantity by the same or different persons. This leads us to two related but different concepts: precision and repeatability. 3.8 Precision. Suppose you want to find the density of a sample of quartz in your mineral collection. Density is found by dividing the mass of the sample by its volume. The measured quantities are mass, 27.55, and volume 10.4 centimeters cubed. When you perform the division on a calcula, torr, the answer is 2.649038462 G SA CM3. As you can see, calculators can compute answers to many decimal places, in this case, 9. But is it proper to report your result to that many decimal places? Look at the data. You measured the mass to 2 decimal places and the volume to only 1. Any digits in the decimal places beyond the given digits are unknown. Do you think the answer to a calculation involving measured data should be more exact than the original numbers? Precision is an assessment of the exactness of a measurement. A more precise measurement has more certain digits than a less precise measurement of the same quantity. The number of digits in a scientific measurement and the location of the decimal point indicate something of the instrument's precision too. The finer the spacing of the graduation marks on the instrument scale, the more digits and decimal places are possible in the measurement and the more exact the measurement. You determine the exactness of measured data by reading the major and minor divisions on the instrument scale. Most of the digits in a measurement come directly from the scale marks. You're certain about these digits. But measurements almost never fall exactly on a scale mark. You must estimate where the measurement falls in between the marks and include that estimation as part of the measurement. This leads to our first rule of measuring. When measuring with a metric instrument, estimate the measurement to 1/10 of the smallest decimal subdivision on the instrument scale. Metric instruments have scales subdivided into tenths, so estimating the fraction of the smallest division in tenths just adds a decimal place to the measurement. This is not true for most instruments measuring in true English units. A foot ruler, for example, commonly has 16th-inch graduations. Estimating a tenth of 16th is not very useful. Users will estimate to a 32nd or 64th of an inch in such cases. Most measurements made in a high school laboratory come from metric instruments. The precision of a measurement is limited by the size of the smallest decimal subdivision on the instrument scale. 3.9 Repeatability. Precision applies to a given instrument, but the data an instrument produces is usually part of a larger, often complex measuring process. Making a measurement involves the instrument, to be sure, but it also includes the operator, the thing being measured itself, and the surrounding environmental conditions. How do you know that any single measurement is actually useful? Scientists evaluate the usefulness of their measurements by repeating them as many times as needed to see how they vary. These variations represent measuring errors from some average value. With enough measurements, scientists will calculate this average, and it becomes the measurement. The differences between each measurement and the average are called random errors. Random errors are more easily detected with instruments that are more precise, but they tend to cancel out when enough data is collected to compute an average. Small random errors mean the measurement has good repeatability. Having a good idea of what the result of an experiment should be is normal for scientific work. If the results of a series of measurements continue to be different from the expected or accepted value, then the scientist begins to look at the measurement process. Similar differences indicate a systematic error, one that shifts the results of measurements the same amount and same direction each time. Systematic errors come from inaccurate instruments, improper measuring methods, or environmental factors affecting the process. These errors are harder to detect in school laboratories. Measurement results may be repeatable, but they could be inaccurate. 3.10 Significant digits. Suppose you use a metric ruler to measure the width of a piece of notebook paper. The smallest divisions on the ruler are millimeters. You carefully position the ruler across the paper and find that the paper is between 215 and 216 millimeter wide. What should you report as? The paper's width? Reporting 215 millimeters wouldn't be correct since you can see that the paper extends a little bit beyond the 215 millimeter mark. Likewise, 216 millimeter would also be incorrect since the paper falls short of that mark. Should you split the difference and report 215.5 millimeter? Suppose the paper ends a little closer to the 216 millimeter mark. Should you report 215.7 millimeters? How about 215.75 millimeter? Or even 215.759, 84 millimeter? Scientists have a way to indicate the precision of their measurements. They use the concept of significant digits, SD. You learned in subsection 3.8 that in any measurement, you're certain of all the digits obtained from the scale markings, but you can only estimate one additional digit. The significant digits of a measurement include the certain digits plus this estimated digit. The only other digits that might be required when recording the measurement are placeholder zeros for locating the decimal point. A measurement of 215.7 millimeter, for example, has 4 significant digits. You read the 2, 1, and 5 directly from the ruler scale. You estimated that the 7/10 of a millimeter and added it to the certain number 215 millimeter. Because you estimated the last digit, any value between 215.0 mm and 216.0 mm would be a valid measurement. Any reading in this range would indicate he corrects significant digits, but the accuracy of the measurement might suffer. Also, reporting more digits, like 215.7 in centimeter with the ruler used in figure 3 to 14, would be wrong since there is no way to estimate the value of a digit in the second decimal place. Since a scientific measurement must include an estimated digit, you suppose that your ruler indicated a reading of exactly 216 millimeters should report the reading as 216.0 millimeter, which includes the estimated 0.10 of a millimeter. Adding a 0 in the first decimal place of the number does not make the measured paper any wider, but it does indicate the precision of your measuring instrument. Not including the 0 would indicate your ruler had only centimeter, 10 millimeters graduations, and the 6/10 centimeters was the estimated digit. Identifying significant digits. How does a scientist know which digits are significant in measurements reported by other scientists? He follows a series of rules for using significant digits. In this course, we provide the following set of rules that are similar to those used by scientists to identify significant digits in measurements. SD Rule 1. SDs apply only to measured data. The numbers below are not measured data. You should consider these types of numbers to be exact or to have an unlimited number of decimal places. Significant digits do not apply to them. Counted numbers. 5 students, 1 pair of shoes, a dozen eggs, 11 players. Pure numbers. 9, 2, n, pi, 3.1, 41, 59. Root 5, 2.2 606. Fractions that are exactly 1 by definition. 60 sec, 100 centimeters, 1852 meters. 1 million, 1 nem. SD rule. 2. All non-zero digits in measured data are significant. 112.54 mir. 5 SDs, estimated to the nearest 0.01 meter. 34 to C. 2 SDs, estimated to the nearest 1 dirc. Measurements that are whole numbers. Where the last digit is not a 0, do not have decimal points. SD rules 3, 4, and 5 describe how to deal with zeros in measurements with and without decimal points. SD Rule 3. All zeros between non-zero digits are significant. 10.6 mils, 3 SDs, estimated to the nearest 0.1 ml. 15.06 m, 4 SDs, estimated to the nearest 0.01 m. 103 K, 3 SDs, estimated to the nearest 1 K. SD Rule 4. Decimal points define significant zeros. ALF, a decimal point is present. All zeros to the right of the last non-zero digit are significant. 45.0s, 3 SDs, estimated to the nearest 0.1 s. 8,500 L, 4 SDs, estimated to the nearest 0.01 L. B. If a decimal point is not present, no trailing zeros are significant. They are placeholders to locate the assumed decimal point. 10 centimeter towards 1 SD, estimated to the nearest 10 centimeter. 120 degrees C, 2 SDs, estimated to the nearest 10 degrees C. 1800 green, 2 SDs, estimated to the nearest 100 green. C. If a decimal point is present, none of the zeros to the left of the first non-zero digit are significant. They are placeholders to locate the decimal point. 0.05 2 SDs, estimated to the nearest 0.001 error. SD Rule 5. A decimal point must follow an estimated 0 in the ones place. If the estimated digit of a measurement is a 0 and falls in the ones place, you cannot tell for sure what the precision of the measurement should be. In these cases, we include a decimal point to indicate that the 0 in the ones place and any 0 to the left of it is significant. 110 mid-charging, 110 m, 3 SDs estimated to the nearest IM. 1000 K, 1000 K, 4 SDs estimated to the nearest 1K. 3 to 11 scientific notation. Measurements in science often deal with very large or very small numbers. Geophysicists have calculated the mass of the Earth to be 5,170,200,000 kilo. Nuclear physicists have determined the mass of 2 hydrogen atoms to be 0.0 674 core kiloharso. Such large and small numbers are difficult to read and write, and even more difficult to use in a mathematical calculation. You can express such numbers much more conveniently in a form called scientific notation. In scientific notation, you convert very large or small numbers into a product of a small number and a power of 10. The symbolic format for scientific notation is mx10, where m is a number greater than or equal to 1 and less than 10, and n is an integer exponent, positive or negative, of the factor 10. Using scientific notation, the mass of the Earth is 5.9722 x 10, 24 power kg, and the mass of a hydrogen atom is 1.674 x 10, 27 power kg. You can see that this is a much more compact way of writing these kinds of numbers, scientific notation and significant digits. According to SD Rule 4B, the measurement 3,800 millimeters appears to be estimated to the nearest 100 millimeters. But what if the estimated digit in this measurement is actually in the tens place? This means that the 0 in the tens place is significant, and the 0 in the ones place is not. So then, the measurement properly has 3 SDs. You can't indicate the precision of this measurement by just inserting a decimal point at the end of the number. 3,800 millimeters. Wrong. In a scientific measurement, the only way to correctly indicate the precision of the measurement is to use scientific notation. Write the significant digits as the factor m in scientific notation. 1 greater than or equal to m is less than 10, and drop the remaining 0. 380 x 10 cubed. M. Right. This method preserves the precision of the measurement in a way that standard decimal notation can't. In this section, so far we have introduced you to the big concepts of accuracy, precision, repeatability, and significant digits. More than anything else, these concepts should show you that even operational science is not about absolute truth. The best we can do is define workable standards of accuracy and precision, and then use tools to help us stay within those limits. 3.12 Math with Measurements. In subsection 3.8, we figured the density of a sample of quartz by dividing its mass by its volume using a calculator. The calculator displayed the answer to 9 decimal places, which was far more precise than the measured mass and volume. See Figure 3 to 17. How do you know how many decimal places to report when performing calculations with measurements? Calculators can give results with many decimal places. However, reporting an answer with greater precision than any of the original data is misleading and not scientifically valid. To avoid this problem, scientists have developed sophisticated methods for identifying the significant digits in calculated results. You can imitate these methods by using some simple rules we have provided in Appendix E. We recommend that you become familiar with the rules by practicing them, since they will be important in more advanced science courses. Solutions to example problems in this textbook will show you how the rules apply. However, you shouldn't get hung up on using the SD rules. Think about how these ideas affect your results in your homework and especially in your lab activities. Don't get bogged down in the details of determining SDs in your answers and miss the big science principles. 313 Using measurements to solve problems. Imagine that you work at Andrew Tool and machining the machinist shop that NASA chose to make some of the most complex parts for the Mars rover Curiosity. How would you make gears with a microscopic precision of 2/10,000ths of an inch, which is much less than the thickness of a human hair? The wiggle room in parts that are made to fit together, like a hole in shaft or interlocking gears, is called mechanical tolerance. Engineers express tolerance as the desired dimension plus or minus, plus, an allowable variation. For example, the diameter of the earbud jack on your MP3 player is specified as 3.60 plus 0.05 in diameter. That means that it could be as small as 3.55 mm or as large as 3.65 mm. Any smaller, and the earbuds won't work. Any larger, and the earbud plug won't fit in the jack. Being able to measure and do math with significant digits is key to designing parts with small acceptable tolerances. But stating small tolerances in design drawings is useless without good machines and skilled operators that can reliably cut, drill, and shape parts. The tolerances that Andrew Toole and machining had to work with were pretty tiny, but they specialized in extremely accurate machining and rigorous quality testing. Another strength that set them apart as a company was the extra human care they demonstrated to get the job done with microscopic precision. And the result? In the weeks after Curiosity's landing, its mission control team was overjoyed that all of its mechanical systems tested perfectly, a tribute to their designers and builders.